Before dipping into angular kinematics, we went over distance, displacement, speed, and velocity. So remember, when we have a direction, that is displacement. Then that is velocity. Change in x without the direction, that's distance. With direction, that's displacement. Speed goes with distance. Velocity goes with displacement. Then we quickly reviewed when distance and displacement have the same magnitude. That is when there are no turns. When there are turns, so for example, if I went north and then I went east, the distance, let's say 5 and 10, the distance traveled is 15, but the displacement right here would be that. This is the displacement because it's the connection between the start and the finish. So distance and displacement when there is a turn are different, and distance traveled is going to be longer than displacement. And then this never happens. You cannot end up farther than you traveled. So your distance is never less than your displacement. So then we went into circular kinematics. So when we go for linear versus circular kinematics, we have x for distance displacement and theta when we talk about angular displacement, angular distance. So in the example below, we have the horse in the merry-go-round that is 4 meters away from the center. If it rotates, the merry-go-round goes around, then the horse is traveling circumferences. Each time there's one revolution, it's 2 pi r, so it's going to be 2 pi times 4. It's 8 pi meters. 8 times 3 is about 24 meters. So then 8 pi, if you use your calculator, that's about 25.1. 25.1 meters. That is one rotation. If there are 10 rotations, that means that the distance traveled is going to be 80 pi meters, or about 251 meters. Displacement, however, so if you start, let's say the horse starts here, 1 rotation, comes back, 2 rotations, and on every time it ends up where it started. So displacement is technically 0. Angular distance traveled, that 1 rotation, now we are connecting 1 rotation not to the circumference as before. For angular, we're connecting it to degrees, or better yet, radian. 1 rotation in terms of degrees is 360. In terms of radians is 2 pi radians. So if we have 10 rotations, that's going to be 20 pi radians. As far as displacement, it's still 0. If we end up in the same place, displacement, angular or not angular, is going to be 0. If we have the time to go with it, then we have the ability to calculate speed. So average speed of a horse is going to be your total distance, 251 meters divided by 20 seconds. Or you could also do 80 pi divided by 20. That would be your 4 pi meters per second. Or if you do 4 pi on your calculator, that's going to be 12.6 meters per second. Average velocity, remember, velocity goes with displacement. If displacement is 0, then the average velocity of the horse is also 0, and you can do meters per second or not. If that is how we figure out the linear speed, distance, linear distance over time, then angular speed, we could do this formula. If you look back up, we had 25 radians for theta. So right here, I'm going to say 20 pi radians as the unit divided by 20 seconds. And that is going to be exactly pi rads a second. So that is your unit for measuring angular speed, radians per second. And then finally, what do we have? The formula right there, theta over t. Now remember how interesting, we had 4 pi meters per second versus pi radians per second. Looks like if we multiply by the radius, if I take this omega and multiply it by the radius, I end up with v. Now, distance-wise, remember how we said each rotation is 2 pi times 4, 8 pi meters. But 1 rotation is just 2 pi. 4 is the radius, and it looks like theta times radius was equal to the length of the circumference. These two formulas right here are connecting our linear and angular terms. Distance in linear terms equals Distance in angular terms times radius. Speed in linear terms is angular speed times radius.